So we're going to be talking about Newton's third law today. Reviewing first law, we use the law of inertia, meaning the net force is zero. What happened is the object will either stay at rest or a constant velocity, or in general, acceleration is zero. So basically, F net equals to zero, meaning all the forces are balanced, the acceleration is zero. So on the question, they can say, oh, the object is traveling at a constant velocity. And then you have to get that, oh, okay. Something traveling at constant velocity means the acceleration is zero. That means the question has kind of not directly, but tells me that all the forces are balanced. Then we went on and talked about the Newton's second law. Second law, in general, you can just say F net equals to ma. If there is a net external force that is not balanced, the object will be accelerating. And we've also talked about a special case for the second law, which is force of gravity. Fg is mass times g, which is the acceleration value for gravity. And the third law, the famous phrase saying is the action-reaction force. For every action force, there is always an equal and opposite reaction force. So I'm going to show you my beautiful artistic ability. Okay, so if I have a wall here and I have this person who is standing on a skate, okay, and this person has a really long arm that can push the wall. The force that this person is pushing, this person is pushing to the right on the wall at 10 newtons. Okay, so that means if I were to draw a free body diagram for the wall feels a force of 10 newtons going to the right. This is the wall. But what Newton's third law is telling you that at the exact same time, the wall will have a reaction force that is the same in magnitude but opposite in direction. Okay, so this is the reaction force from the wall. I'm just going to change this. This is the action force. Okay, so this is the action force. And the third law is saying it's the same thing. But the key thing is, now this blue force is actually not acting on the wall. It's actually acting on this person. So if I were to draw a free body diagram for this person, this person feels the 10 newton that is going toward the left direction. So if I were to draw a free body diagram for the person actually feel this way. So number one thing, the action and reaction force are the same magnitude, meaning the same number, opposite in direction. And the key second thing is they're not acting on the same object. Okay, one is on the wall, one is on the person. And that's why if you push this way, you're going to go towards the left hand side, because what's really acting on you is causing you to accelerate to the left. Applications of the third law. Okay, basically any motion, you can't walk. When you walk, you push backwards, you move forward because the ground is pushing forward towards you. So say swimming. If you're swimming, your leg kicks backwards on the water. The water pushes you forward, and this is why you are moving forward, because it's how the water is pushing on you. Okay, helicopter. The blade exerts a force downward on the air. So what's the air doing? The reaction forces the air. It's going to push you upwards on the blade. That's why the helicopter goes up. You have a squid. It pushes water backwards. So what's the water doing on the squid? It's pushing it forward. Okay, so this action force, it's saying that if I have a tractor, the tractor exerts 200 newton west on the trailer. Describe the reaction force. Okay, so a lot of time I just like to write it out. Okay, so tractor exerts 2,000 newton west on the trailer. Your reaction force, it's always going to be opposite in direction. So it's going to be going to the east. And then what you do is you basically take your object and you swap them. Okay, so instead of the tractor exert this, you now have the trailer exert 2000 Newton each on the tractor. Okay, so tractor and trailer. Okay, so it's being hooked up like that, right? So the trailer, it's feeling the pull forward. Okay, so this is the 2000 Newton to the west. But at the same time, what happened is the trailer also pull backwards this way on the tractor. That's why you feel the drag, right? Like when I'm pulling the trailer is dragging the tractor backwards, right? So that's why they're pulling. That's the action reaction force. Okay, a ball hanging on a string. So when you have question like this, the best thing you can do is you actually want to start with drawing the free body diagram. Okay, that's your first step. So let's draw this. Okay, something is hanging on a string, so I know that there is a force of tension. And I also know there is force of gravity. Okay, so what does force of gravity means? Force of gravity is the earth pull whatever the Newton is downward on the ball. Are we okay with that? That's the action force. And then that means opposite to that, if this is the action force, what's the reaction force? The reaction is going to be opposite in direction. Okay? And you swap the two objects. At the same time, the ball is going to pull whatever the Newton upwards on the earth. But the reason why the earth doesn't seem like it's moving towards the ball is because the earth is a lot more massive, right? But the forces is actually the same magnitude, okay? And if you recall from Newton's second law, F equals to ma, if it's the same force, but if I have a super big mass like the earth, remember we said the acceleration would become really, really small. That's why you can barely even notice it, okay? All right, so what does force of tension means? Force of tension is the ceiling. I'm going to change color. Okay, so the ceiling pulls upwards on the ball. So opposite to that, we're going to swip the direction to a down, and we're going to swap the two objects. But at the same time, the ball will pull downwards on the ceiling. Okay, so what that means is with every single force on the free body diagram, you would write out the action and then the corresponding reaction force. Would the sailboat work better with the fan? If you have a sailboat and if it doesn't have a fan, okay, if you only have the sail, what happened is the wind will blow on the sail. At the same time, the sail will move backwards to the air, pushing it forward. So this is the force that's actually acting on the sail, right? So that means the boat is going to start moving this way. But now you have a fan. Okay, the fan is going this way. This is the fan, sorry. Okay, when the fan blows to the right on the sail will push back left to the fan. Will it help with the moving or not? No, it will not help. It would only help if we turn our fan backwards and actually turn the fan going this way, because if the fan is going to the left, what happens is the air will start pushing forward, helping it goes. All right, now math question. Assume the card below has a mass of 1.2 kilogram and the ball has a mass of 0.072. During the short time of interval the spring is released, the horizontal force on the ball is 1.8 Newton to the east. Identify the three action-reaction pair force involving the cart as the spring is released. Okay, so draw your free body diagram. Okay, so if this is the this is gonna has to be separate, right? Because the spring will push onto the ball, but the ball will also push back onto the spring, and that's the action reaction force. So if this is talking about the ball, okay, the ball is going to feel a force on the spring. This is the applied force. This applied force is the force of the spring going east at 1.8, I should say 1.8 meters per second east. 1.8 Newton to the east on the ball. But at the same time, your cart is going to feel the backwards. It will have the force of the ball, the force on the ball, pushing 1.8 Newton to the west on the cart. So this is the first pair of action-reaction force. The second action-reaction force has to do with the other parts of the of any of the free body diagram. So I'm going to change color. I'm only just going to finish the question for the ball. The ball has the FG, right? And then this is going to be kind of the similar type of question we're doing from this question. Like it's similar to this. So we're going to first of all write out the action force. So the force of gravity, what really force of gravity for this is the force of the earth pulling downwards on the ball. But at the same time, the reaction will be the ball will be pulling upwards on the earth. Okay, the third pair of action-reaction force, I'm going to be talking about the force of normal on the cart. Okay, so the Fn, I'm not going to do the force of gravity on the cart. It's going to be the same idea as the ball, but instead of it's just the cart. So how about the force of normal? I can still write the Fg here. Okay, force of normal, the action-reaction force will be the force of the surface acting upwards on the cart, but at the same time the cart is going to push downward onto the earth or onto the. And the last question is draw a free body diagram for the ball, which we already did, but let's just do it again. Okay, it's going to have force of gravity that's acting on it, but at the same time it is going to have a rightward force. Okay, it's going to have a rightward force from the spring, which from the question it tells you is 1.8 newtons to the east. And the other thing that I'm going to note down is the mass of the ball, which is 0.072. So because this is the ball, I'm going to use the mass, right? So this is for the ball. Okay, and the net force, we're going to calculate the acceleration while the spring is pushed. We know that F net is going to equals to ma. When they require force and acceleration, this is the equation that we're using. Okay, and the F net is going to be, and we're only going to focus on the x direction. So the net force is 1.8 to the east, and the mass is 0.072 times a. So rearrange the equation. I'm going to divide both sides by the 0.072. So a is 1.8 divided by 0.072. So I got an answer of 25 meters per second square to the east. So that's going to be the acceleration of this ball. That is